Thank you very much. So thanks for attending this talk, even after attending the first one. So in the previous, in the first lecture, we have started with the basis of conformal field theories. We studied 4-point correlators of identical scalar operators. We have seen that those were described in terms of a function GUV of the cross ratios. And we have also seen that this function admits a decomposition in terms of conformal blocks with some square OP coefficients. And then we have studied, sorry, you put it over here, you put it over here. Then we have studied some properties of the conformal blocks. Now, on one hand, the conformal blocks, they have the following small u behavior. So they go like u to the tau over 2, where tau is the twist, the dimension minus the spin. And we have also seen that in the small v behavior, they diverge, but only logarithmically with v, as v goes to 0. Then we have studied this very simple model, given by generalized free fields. And in generalized free fields, the 4-point function is simply given by this very nice sum of 3 terms. And then we have, well, I told you, but it's something that you can do at home. We have done the conformal partial wave decomposition of that. And we have seen that the intermediate operators of generalized free fields are double trace operators of the form, so this is the 4-point function 5, 5, 5, 5. And the intermediate operators appear to have dimension minus a spin, which is equal to the twist, remember, 2 delta phi plus 2n, so they are of this form, phi box of n, d mu 1 up to d mu l, acting on phi. And in a free theory, in a Gaussian theory, the dimension of these guys is equal to this thing here. And we saw this precisely from the conformal block decomposition of this very specific example, generalized free fields. Before I start with the lecture of today, are there any questions? Good. I mean, something that I wanted to, so discussing with the students yesterday, something that in order to appreciate the difficulty of conformal field theories, usually when you have an expansion like this, you don't know what the spectrum of your theory is. So here, both the range of the sum as well as the OP coefficients are usually unknowns. So this is quite complicated in general, but for generalized free fields, we know what the spectrum of your theory is, because the theory is basically free, and this is the spectrum with some OP coefficients that you can compute, and we denoted them by A, G, F, F. Is that okay? So we will start the lecture of today by having a look at a puzzle. And the puzzle is the following. Even in this super simple model, which is generalized free fields, already something interesting is going on. Because if you look the right-hand side, each conformal block on the right-hand side diverges at most as log p as v goes to 0. So we look at this equation, and we study it. We see what happens as v goes to 0. And we see that on the right-hand side, each conformal block diverges logarithmically as v goes to 0. But on the left-hand side, we have a power law divergence. Now, yes. Yes.
Those operators, those are symmetrized traces.
Yes, absolutely, absolutely. So, if you want to be, I can be as precise as you want.
Yeah,
but I am super precise. So,
you can just say it.
Okay. So the thing is, of course, you will have these derivatives can act on many of these. So actually, sometimes people denote it like this, so they can act on both ways. And you, of course, you are looking at the primary states. So some of these combinations will be descendants. Then you need to look at the primaries. And the primaries are given, for instance, well, you can actually see which combination. So the derivatives can act on both. So this is
the coefficients.
absolutely. So you can fix the coefficient. For instance,
So
if you have
carry on.
yeah, good. Now, of course, you know examples of these things happen. For instance, imagine that you do the sum of x to the n over n factorial from n from 0 to 2. This is a polynomial and diverges like a polynomial as x goes to infinity. I will have another example. N goes from 0 to 10 to the 10. This also diverges as a polynomial as x goes to 0. It's a very big polynomial, but it diverges as a polynomial. However, if you have the sum to infinity, this is e to the x and diverges exponentially. So the answer, of course, is that here on the right-hand side, it is true that each conformal block diverges logarithmically, but we have an infinite number of them. So the correct way of taking the v going to 0 limit is not block by block, but first we need to do the sum over L and tau, and then you take the limit as v goes to 0. So this is only possible because on the right hand side we have an infinite number of operators. And this, if you want to do it, if you want to do a super transparent computation and to see what is going on, so this is something that you can try at home. What you do, so the best thing to do, is you take the sum of generalized free fields, and then, you can see, right, if I write here, and then you take the limit u going to 0. Now, if u goes to 0, you may recall that these conformal blocks were approximated by the so-called collinear conformal blocks, which are functions of v. And then what you get in the limit in which u goes to 0, on the left-hand side, you get u to the delta phi, I am cancelling the 1 on both sides, plus u to the delta phi divided by v to the delta phi is equal to the sum only over the spin. Because notice that this has a power u to the tau over 2, so that if I am taking the limit u going to 0, I keep only the double trace operators with the smallest twist. So in general, tau is 2 delta phi plus 2n, but if n is higher than 0, this will be subleading in the small u. So I am just looking at these double twist operators, so I have to sum only over the spin, and then we have sum a, L, GFF, times u to the delta phi, f to delta phi L, collinear v. And just for you to be very happy, I will recall the form of these collinear blocks, which we have seen yesterday. And remember that these collinear blocks were given by 1 minus v to the L times a hypergeometric function to f1, delta phi plus L, delta phi plus L, 2 delta phi plus 2L, 1 minus v. And so here, this is everything you can put in your computer. You can play as much as you want with this. So these are all expressions known in Mathematica. You can see that each hypergeometric function diverges as a logarithm as v goes to 0. However, the OP coefficients of generalized free fields, so these coefficients here, I didn't give them to you, but let me give them to you. They are a bit complicated, but with a few hours of work, you can guess them. Maybe a few days. Plus 1 gamma squared. And it is a beautiful property of hypergeometric functions. They admit this integral representation. And if you take this, I was going to say crap, but that's a not very nice word. So if you take this very complicated expression and you put it here, you use the integral representation, you can do the sum, and now you can take the limit v going to 0, and indeed, you see that it goes like 1 over v to the delta phi. Is that okay? Yes. So, and something that we learn from this expression, is that the divergence arises from the large L region. Indeed, if you were to truncate the sum at any spin, even 10 to the 10, as in the polynomial example I was given, this would diverge only logarithmically. So this power law here arises from the region in which the spin is very large. Is that okay? Any questions about this? You mean like here in the blackboard for you?
No, but in principle, taking the large and...
Yeah, that's not that easy, but yes, you can do that actually. And yes, let me tell you actually what the result of this is. So what happens with this hypergeometric function, you can use an integral representation, and in the limit in which L is very large, this becomes a Bessel function. And then you can do an integral over the Bessel function. For that, it's very important that you take this prefactor into account. And from that, you get this integral, and you can show that the final answer is 1 over v to the delta phi. It's funny you ask, so that is in a footnote of a paper we wrote with Juan like 10 years ago, in another problem, like we were talking about something else. Yes, but you can do that. But it's a beautiful computation, and it shows how you can get this enhancement of the divergence of a single conformal. Is that okay? Good. Any questions about this? So this is like the simplest model that you can consider in a conformal field theory. So it is basically a free theory, and of course most theories are actually not free. So now we are going to go back to our bootstrap equation, and we are going to have a look at the bootstrap equation for a completely general. Yes?
But since Alday asked the question with n, so where does n, the number of free fields, appear?
The number of?
Free fields, of generalized free fields.
So it's just phi. And
You have one.
yeah, it's just phi. So, sorry, so the external field is phi. And the double trace operators in between are like derivatives of these acting on two phis, such that they have to be not descendant. Is that okay? Yeah? Yes, that's right. And good. So now let's have a look at a completely general conformal field theory. And let me stress the fact that the equation I am going to write is the equation we have derived in the previous lecture, valid in any number of dimensions for any conformal field theory. So, the bootstrap equation or crossing equation was b to the delta phi times 1 plus the sum over tau and L of this c tau L squared u to the tau over 2 f tau over L uv, and this have to be equal to u to the delta phi 1 plus sum over tau and L of C tau L square V to the tau over 2 F tau L of V and U. And as we mentioned, this is an incredibly complicated equation because we don't know what the spectrum of the theory is. So we have no idea what these sums run over, and we don't know what the OP coefficients are. So it looks a bit hopeless. Now, what we do, so first, we have a look at this equation, we panic a little bit, we cry, and then after that, we say, well, we can take the V going to zero limit. If you take the V going to zero limit, and before you can use Mathematica, and you can show that the equation I wrote is equivalent to this. And now if you take V going to zero limit, what do we get? Well, let's say here on the left, we keep this. C tau L square, U to the tau over 2, F tau L, UV. And what do we get here? Now, here on the right-hand side, as V goes to 0, the leading contribution comes from this innocent 1, which was the identity operator in the dual channel. So this is U to the delta phi over V delta phi, 1 plus, and notice that the power of V of the operators on the right is dictated by the twist of the operator, because we have V to the tau over 2. Okay? So, the next term is of order.
You could explain that in the region where V goes to 0, this F goes as a logarithm.
No? Sorry. Yes? Sorry. So, let me be clear. So, F of UV as U goes to 0 goes like U to the tau over 2, and as V goes to 0 goes like log V. But here we have F of VU, right? Here we have F of VU, and we are considering the limit in which V goes to 0. So in the dual channel, since we have F of VU, we know how that behaves. It behaves like U to the tau over 2. Is that okay? Because we are exchanging V and U.
So like V tau.
Yeah, it's V. Sorry, R is my U and V very similar.
That's okay.
Yeah. So it's V to the tau mean over 2. Where this tau mean is the tau. So let me tell you a little bit about this. I don't think I need this. But let's talk for 30 seconds about what this tau mean can be. People seem to like unitary representations, as you may have gotten an idea over the last few lectures. So, what we will be assuming in this talk is that tau mean is bigger than 0. When in a conformal field theory, you have that the tau, so the twist of the identity operator, the identity operator has delta equals 0, L equals 0, 0 minus 0 is equal to 0, so tau is equal to 0 for the identity operator. The next operator will have some tau, and we would like to say that this tau has to be bigger than 0. Why? Because I want this term to be smaller than this one. And when does this happen? There is when this happens, we say that the theory has a gap in the twist. And there is a unitarity bound that you can prove. And the unitarity bound tells you that tau is bigger or equal than d minus 2 over 2 for a spin equal to 0, and d minus 2 for a spin equals 1, 2, etc. So you see that if d is bigger than 2, which is the most interesting case, or the case we are interested in, then we have always this gap. Is that okay? So in dimensions higher than 2, we have this gap, and this term is much smaller than that one. Is that okay? But the beautiful thing then is that this equation is general for any conformal field theory in dimensions higher than 2. We have not assumed a Lagrangian description, we haven't assumed supersymmetry, we have not assumed weakly coupled. Any conformal field theory in dimensions higher than 2 will satisfy this equation.
Have you assumed Lorentzian versus Euclidean?
Sorry?
Have you assumed Lorentzian versus Euclidean?
Yes, actually, and that's a bit subtle. And I will explain it with pretty pictures on my last talk tomorrow. But basically, I can tell you a little bit now, but I would confuse a lot of people. But okay, that's maybe okay. So if I want to play with these cross ratios, U and B, as I am doing here, I need to do that in Minkowskian signature. And I will draw pictures tomorrow, but basically in Minkowskian signature, I can play the game of taking V small, keeping U arbitrary. That you do. I will show tomorrow why you can do that, but yes, that will be the answer. Now, here we have a puzzle, if we have a look at this equation, and the puzzle we have here is that the right-hand side, as V goes to 0, diverges as a power law. However, on the left-hand side, as V goes to 0, each conformal block diverges as the log of V. It would have been nice if we would have seen some example in which that happened. And indeed, that is exactly what was happening in generalized free fields. So, from our example of generalized free fields, we have learned that the only way in which we could match divergences as V goes to 0 is if we have an infinite number of operators but furthermore, we have also learned that this divergence arises from the large spin region. So now, what we see, actually by looking at the powers of U on the left and on the right, we see that we need an infinite number of operators whose twist approaches to delta phi for large spin. Simply because we need that these log V's sum up, add up to some 1 over V divergence, but that we only get with an infinite number of operators. And the powers of U, just matching the power of U on the left and on the right for a small u, tell us that this has to be 2 delta phi. Now, this may not happen for all operators, but it has to happen for operators with arbitrarily large spin. Is that okay? So, we deduce actually from this that there should be this tower of operators whose twist, or the dimension minus the spin, has to be 2 delta phi plus something that vanishes as the spin becomes very large. If you do something slightly more advanced, it is very easy to show that actually you need towers of operators that behave like 2 delta phi plus 2n plus something of order of 1 over n. Now, the next question is, what are the OP coefficients of these operators?
Question.
Yes.
How do you know that's 1 over L and not 1 over squared of A or 1 over L squared?
I know precisely, it happens to be 1 over L squared. I can tell you a lot about this. Yeah, so what the precise power here is depends on this tau mean. And this basically 1 over L to the tau mean. Yeah, it's a good question, and that's the answer. Now, the second question is, well, we are excited because this is kind of the delta, at least for large spin. What are the OP coefficients? And we have found an example such that if you take these generalized free coefficients and you plug them into the conformal block, you precisely get this 1 over B to the delta phi, which is exactly what we need to get here. So these operators not only have that spectrum, but also have some OP coefficients, let's call them like this, which is generalized free fields times 1 plus something that goes actually as 1 over L squared, like this. Now, I want to stress how remarkable this is. The only assumptions we have done, we have a conformal field theory, any conformal field theory, in dimensions higher than 2, and the only thing we have assumed is that in the dual channel there is this 1, but this one just arises from the identity operator. So, just from the existence of the identity operator, together with crossing symmetry, we derive the following beautiful result. Any conformal field theory with O in the spectrum, so if O is in the spectrum, then it should also have, with some phi, sorry, if phi is in the spectrum with some delta phi, then it also should have infinite towers of primary operators with arbitrarily large spins and whose dimension goes like this and OP coefficients go like that. Period. That's a general result about the spectrum of conformal field theories in any number of dimensions. No supersymmetry, no planarity, anything. Just conformal symmetry. Any questions?
Yeah, so the issue of strongly coupled or weakly coupling, nothing is here.
Absolutely, yeah, I don't care. Yeah, exactly. Yeah, we never use that the theory is weakly coupled or strongly coupled. And this is true for any conformal field theory in D bigger than 2. There is something, also something quite cool. We have seen that this works only if we have an infinite number of primaries. And in 2 dimensions, for Virasoro primaries, it's not the case. So we see that in higher dimensions, you necessarily need an infinite number of primaries. Is that okay? Yes? Oh, so there are 2 questions.
Sorry, Fernando, I missed your answer to Vishnu's question about the signature, Lorentzian versus...
Yes, so as you will see, so I will be more specific tomorrow. Will you be tomorrow? Yeah.
Yes.
Yeah. So we will see that in these things of the analytic bootstrap, it's nice to study the correlator in Euclidean signature. And what happens, well, I can tell you now quickly, but basically you can introduce coordinates in which U is z bar and V is 1 minus z bar. And if you are in Euclidean signature, Z and Z bar are complex conjugate of each other, and you can study the point at which U and V are equal to 1/4. And that's the Euclidean approach, and that's what people does. Now, in Minkowskian signature, Z and Z bar are independent real variables, and we can go to a limit in which Z is very small, but still V doesn't have to go to 1. And I will show that again tomorrow. but basically being in Minkowskian signature, you can explore regions of the cross ratios that you cannot explore in Euclidean signature. But these are the regions that we need to explore. Physically, and I am kind of spoiling the fun for tomorrow, but physically, if you have a correlator, all space-like separated, and you take a limit in which the things are null separated, this correlator develops some singularities, and these are this 1/v singularities.
So I was going to ask if this is related to David-Smith differences.
Very much, yeah.
Okay.
Yes. So it's related to Caron quote, and
Right.
yeah, that's right.
Yeah, I have a question.
Yes. Sorry.
So in 2 dimensions, the Virasoro algebra is a lot bigger than.
Yes.
So you do have an infinite number of quasi-primes.
Absolutely. And all this also applies for that. And you can do things in 2 dimensions. Absolutely. So you could forget about Virasoro symmetry, and you could just use conformal symmetry in 2 dimensions, and things more or less go through. It's just cleaner to say d bigger than 2 because you have a gap automatically. Yeah, but indeed, I mean, you could look at 2 dimensions, and you could just use the conformal symmetry. And it's still true that you have an infinite number of quasi-primes. Yeah. Any other questions? Good. So now the idea, so basically the idea that we want to, so the next subject, the next thing that I would like to discuss is the idea of large spin perturbation theory. And the idea of large spin perturbation theory is some method to be able to compute these 1/L corrections to the OP coefficients and the scaling dimensions. And the method will be so powerful that it will allow to compute all orders in 1/L. And as we will see, it will even allow to resum things exactly in the spin. So we are going to get there soon enough. But the basic idea of this, so we want to exploit the, the following idea. So the idea is that if you have the sum over tau and L of some A tau L, U tau over 2 conformal blocks, and on the right hand side we have seen that you have this plus dot dot dot, so this could also diverge. The idea is that the behavior of CFT data on this side at large spin will be in one-to-one correspondence with the enhanced divergences as v goes to 0. And by enhanced divergences, I mean basically with respect to a single conformal block. So a single conformal block has a log v divergence, so any divergence higher than that will give us information about the large spin, the CFT data on the left, so dimensions and CFT data of the CFT, of the thing on the left. Is that okay? At large spin. Is that okay? Good. So we will study this problem because I want to be super explicit. So actually these things you will be able to do them at home. So I will give the following example. And we will study this problem in the small u limit. In the small u limit, already we have all the ingredients that we want. And then our aim is the following. So if you take a small u limit, remember, so let me erase here and take the small u limit on both sides. So, the problem we will have is the following. You have sum over the spin of some coefficients AL times the collinear conformal blocks, which are 1 minus b to the L, 2f1, delta phi plus L, delta phi plus L, 2 delta phi plus 2L, 1 minus b, and this thing has to be equal to some enhanced divergence. So for instance, for generalized free fields, this was equal to 1 over v to the delta phi. But of course, if the theory is not free, if it is any random theory, you will also have the next operator. So this could be 1 over v to the delta phi over 2, or it could be 1 over v to the delta phi minus 1, etc. And the problem we would like to solve is, given the right-hand side, find AL. So given the right-hand side, given the enhanced divergence here, so we can call this h of b, you have to find AL such that this is true. Is that okay? Good. So the trick of this so let's first put some notation here. Let's call this h of b, and this could be 1 over b to some power. For instance, in other interesting things, this will be, in some interesting applications, this can also be log square of b. So also log square of b diverges faster than a single conformal block, and we also would like to get this sort of results. And the idea of this, so I give you h, you have to give me what AL is. So it's this very simple problem. And the idea of the problem is the following. So, the first equation we have, imagine that I am very nice, right? If I am very nice, which I am not, so let's introduce some notation here, FL collinear of V. If I ask you to solve the problem for this example, so let's say AL, FL collinear V equals 1 over V to the delta phi plus something regular. So I never put regular things. Can you tell me what is the answer for AL for this problem? It's just generalized free fields, right? So this, the ALs, that, so this is exactly the divergence. Do you remember? U over V to the delta phi is exactly the divergence of generalized free fields. So if I put here GFF, then this is true. Is that okay? I see puzzle faces. Is that okay for students? Yes. So if here you are given 1 over V to the delta phi, you know what the answer is, because that's the only example we know. So it's this generalized free fields. Then, the second thing we use is that these conformal blocks, so I didn't need it so far, but these conformal blocks are actually eigenfunctions of a Casimir operator. And so there is a second order operator. You can see in many ways, but the idea is that there is a second order operator which we call C, and C acting on FL collinear V is equal to some eigenvalue J squared FL collinear V. Now this C is just a second order operator, so basically so conformal blocks, they are eigenfunctions of these second order operators in both U and V. We take the small u limit of that. And if you take the small u limit of that, you get a very cute operator C, and this operator C is 1 minus V squared, derivative with respect to V, V, derivative with respect to V. And it's fascinating. If you take this hypergeometric function with this factor and you act with this, you get back the same hypergeometric function, and the eigenfunction J squared is equal to delta phi plus L, delta phi plus L minus 1. So it's just something, it's a function of L, and the important thing here is that this grows like L squared when L is very large. Is that okay? Good. But now we say, but if this is true, and this is also true, no one prevents me from getting another relation. And the other relation that I get it by acting on both sides of this equation with the Casimir operator, right? If I do that, what do I get? I get sum over the spin of, for instance, J squared GFF, where this J squared is this very specific function of L. And this FL call V. Why? Because when I hit the left-hand side with the Casimir operator, for each conformal block, I produce a factor of J squared. That depends on L through this. And on the right-hand side, what do I get? I get C, which I just gave you, acting on 1 over V to the delta phi. And this is a very nice computation you can do, and you can see that this goes, well, there is some delta phi squared, it doesn't matter so much, but it goes like V to the delta phi plus 1. This is really cool, because it means that if I am a little nasty, and instead of giving the right-hand side 1 over V to the delta phi, I give you 1 over V to the delta phi plus 1, you know what to do, right? You say, instead of the first relation, I use the second. And I know that the AL I need in this problem is just AL GFF times J squared. Is that okay? Good. So, yes?
Okay, so you can keep on acting.
Absolutely. Absolutely. Now, there is a fascinating thing, and it's the following. Yes? So you can keep on acting. And let's say this function, you call it like H1, or H0, sorry. So this is just a function of generalized free fields. This, you can call it H1, V. And in general, the kind of equations that you will get is that L, JL to the M to the 2M, AL GFF, FL collinear V, is obtained by acting M times with the Casimir operator on 1 over V to the delta phi, and this we call HM V. Is that okay? So, we are very happy. So we have this large list of relations. a beautiful thing is that this largely list of relations, of course, the easy thing is to take m equals 0, 1, 2, 3, but notice that you could also take m equals minus 1. So, by definition, h minus 1, v, is the function such that if you apply the Casimir operator, is equal to h0 of v. Is that okay? So you see from here that if you act, with the Casimir operator on hm, you produce hm plus 1. Is that okay? So, simply because hm is defined like this, right?
I'm not used to Casimir serving as a raising operator.
Yeah, but it's just an operator,
Yes, yes.
right? It's a second order operator,
Okay.
and and one can do that. Is that okay?
And this kind of inverse, it acts nicely on the F curve.
On F curl, it acts just by multiplication of j squared.
No, but the inverse.
2 is 1 over j squared, right?
Okay.
And now we do something kind of nuts, but which you can do. You can analytically continue on m. And it turns out that these functions, you can find them for all m. Not necessarily integer, not necessarily positive. You can find it in different ways, in different expressions. You can actually do that. Okay? But now, we are done. Because we go back to this problem, right? We go back to this problem, and I tell you, aha, I know how to solve that problem. I just take your h, whatever it is, and I write it as a linear combination of my beloved h. Yes?
So just quick, what's the structure of your eigenfunctions in the complex n plane?
Yeah, so it's not easy to answer. It's a bit complicated. Now, for what we do, so for the applications to conformal field theories, we will only need this for negative values of m. And for negative values of m, I can explain. So roughly, it goes like 1 over v to the delta phi, I think plus or minus m, h1, yeah, plus m. And then it admits an expansion in powers of v. And notice, for instance, so just is a very nice feature, you could, for instance, get also things like log square of v by taking derivative with respect to m and then setting m to some value. And here, you would do the same, and this could correspond to insertions of log j. So, the statement is that all these hm, analytically continuing m, give me a complete basis of functions, and then the only thing I have to do is the following, is I look at this h here, and then I say, well, I write this h as a linear combination of my h there, so let's say that this one is h0, v plus 2 times h minus 1, v plus 3 times h minus 2v, right? It will be some linear combination of the functions I know. And then, once I do that, I can immediately tell you that AL is equal to AL generalized free fields 1 plus 2 divided by j squared plus 3 divided j to the 4.
Sorry, is that
Yes.
obvious why the HM is a formal complete?
No, it's not. Well, It is, but it would take me a little while to explain. So it has to do, if you use the structure of conformal field theories and the kind of things from where this has to arise, then you can see. However, so you could also have, so let me give you another example. So you could also have, for instance, h of, sometimes it doesn't have to be integer. So it could also be the number of dimensions d, for instance, minus d, and then here you get 1 over j to the 2d, etc. So you could have also things that are not integers, as here. So in general, you can have harder things.
Sorry to insist, but out of curiosity, the C minus 1 as it acts on F collinear L of V, this hypergeometry that you know. So do you know the expression of differential operator representing C minus 1?
Yes.
How does it do?
Oh, you have to invert. I would need Mathematica. I mean, you need to invert C acting on a function h equals to this.
No, but I actually see, as you define it, as acting on F called A. The function of FV.
Oh, this is just,
the hypergeometric, yes. So you know this operator, you go, it becomes 1 minus V squared.
yeah, and you just act here, and you get back to itself.
So now, but the inverse of that differential operator.
The what? The inverse.
The one that gives J minus 2 as acting on F.
Actually, what I say is I do the other way around. So assume that you have something such that 1 over j squared AGFF is equal to some function, and then I act on C with that.
Okay, so you want to avoid this issue of...
Yeah.
I understand.
Is that okay? So the statement is, so what I want to, so I will, if I have 10 more minutes, I will do something, but basically the statement is that this large spin perturbation theory, so this method, if you know what these enhanced divergences are on the right-hand side, then you can fully write down AL as a series expansions in 1 over L. Remember that this J is basically, J squared is like L squared. Is that okay? Now, so from this, with the method of the right-hand side, we can derive AL as E GFF L 1 plus some coefficient alpha over j squared plus beta over j to the 4. This may have more things like non-integer powers, log j, etc., but all of that can also be derived. Is that okay? Now, what we are going to do now, so the last bit, is, so we have seen that this method allows to determine these OP coefficients for given the enhanced divergences of H. Mathematically, so let's try to be slightly more precise. Mathematically, to have an enhanced divergence is the same, is equivalent to have what mathematicians call a double discontinuity. And the double discontinuity is not scary, it's something actually neat. So you compute 1 or 2 and then you say, okay, that's it. The double discontinuity of this function of v, and it's the double discontinuity around v equals 0, is h of v minus 1/2, and then h of v going around 0 in one direction, plus h of v going around 0 the other direction. And let's give an example. Let's give an example so you see how you calculate this. So imagine that h of v, that we want to compute the double discontinuity of log of v. Well, h of v is just log of v minus 1/2. Now, do you remember the discontinuity of log of v as you go around 0? Do you remember what it was? Is this nice? is 2 pi I, absolutely. So this is log V plus 2 pi I. And here, you need to do the same the other way around. So it's plus log V minus 2 pi I. And if you do the computation, you get 0. Beautiful. Log V is exactly what a single conformal block was giving me. So indeed, a single conformal block doesn't have any enhanced divergence. Happy, we are happy. Now, imagine that you compute this for log square of V. You do exactly the same. So you have log square of V here. Then here, you replace log V by log V plus 2 pi I, but this is the square. And this is also the square. And now, you don't get 0 anymore. Actually, you get 4 pi squared. Beautiful. Log square of V does have enhanced singularity, and that's the singularity that we talk about. You could do also a lot of other examples. For instance, you could do, can I take 1 extra minute to show 1 extra example?
You said you have 5 minutes, so you can carry on.
Well, I was asking an extra on top of that.
Oh, sure. Please do.
So for instance, if you have 1 over V to the delta phi, right? What you do is the double discontinuity is defined as 1 over V. So it's a bit easier to do like V to the alpha for a non-integer power alpha. And this is V to the alpha minus 1/2. And notice that when you go around V equals 0 by 2 pi I, this acquires a phase e to the 2 pi I alpha plus V to the alpha e to the minus 2 pi I alpha. And this here, you can do the computation, and it's sine square of pi alpha. So that for alpha non-integer, 1 over V to the alpha also has a double singularity. Is that okay?
For the V to the alpha.
Sorry? Yes. Yes. Good. So now, we are going to assume, so with the idea of acting with the Casimir operator, let's be super optimistic, and let's assume that if you have this problem here, there is a kernel such that AL is equal to the integral between 0 and 1 of dV times some kernel, which is a function of V and the spin, acting on H, but if you want to be more precise, it should act on the double discontinuity, as I just defined, of this H. So we will just assume that such a thing exists. So there exists a kernel, maybe very complicated, but the kernel is such that if you take H and you plug it here, you get the AL. Basically, what this expression would be given is the resummation of large spin perturbation theory in an automatic way. I was doing it by 1 over J, trying to guess after like 30 terms, and yeah, but people smarter than I came up with a better way. Good. So what do we do? A beautiful idea that you can do here, as before, let's act with the Casimir on both sides. Because if this equation is true, it should also be true the fact that J squared AL is equal to the integral between 0 and 1 dV of K BL, double discontinuity acting on the Casimir, acting on this H of V. And just playing a little bit around these things, it is not hard to see actually that this Casimir, you can take it outside the double discontinuity. So these are two things that commute. So we arrive to this equation. Is that okay? And now, this looks very similar to an inner product. And you remember that when you have an inner product, you can define an adjoint operator for students. So this is a little computation for students. So if you have, imagine that you have an integral, I'm going to say something really deep, of h of x, g prime of x dx, right? And imagine disregard boundary terms. So here is some operator, in this case dx, acting on g. But by doing integration by parts, you can also write this as integral of h prime g of x. So, by doing integration by parts, we have moved the operator that was acting on g, and now the operator is acting on h. It's just integration by parts. We do the same here, and we say, aha, so this is equal to the integral between 0 and 1 of dv of this c dagger, which is easy to compute actually. It's very similar to C with some signs, acting on double discontinuity of h of v. But then we stare at these two things. We stare, yes, thank you. We stare at these two things, and then we say, if these two equations are true, and this is supposed to be true for any double discontinuity of any h, then it should happen that C dagger acting on my kernel is the same as J squared acting on the kernel. Right? Simply because I could also simply multiply both sides by J squared. Right? And you would get the same result here, but J squared acting on K here. And this, you go to Mathematica and you just solve it. And you find an answer. I can tell you the answer if you wish, because it's quite pretty. And what the answer is, so let me do this. And the answer is that this K is 1 minus B to the h bar minus 2 to f1 h bar to h bar 1 minus b, where j squared is defined as h bar minus 1. So if you introduce the notation j squared equals h bar minus 1, the solution to this equation is exactly that hypergeometric function. So we have either large spin perturbation theory or this inversion formula, whose derivation actually is very similar to the idea behind large spin perturbation theory. If I give you a singularity, then I am able to say what the CFT data for these operators are. Of course, what the singularity is depends on the model we are studying. So in the next lecture, we will study a model. Another thing that I would like to say is that notice that if you have a 1 over L expansion, you could also add things that are, for instance, different from 0 only for spin equals 0. We will have some ambiguities too. So this is plus ambiguities in both using the inversion formula or using large spin perturbation theory. We will come back to that. But now the idea is, so let me just write down the last line. So the idea of the method is the following. Is choose your theory, or choose your fight. So what you want to compute in which theory. Then, for that, determine the structure of divergences as v goes to 0, which we have seen crossing symmetry, the existence of the identity operator, etc., are very useful on that. And then use either large spin perturbation theory or the equivalent inversion formula to fix the CFT data. And then you can celebrate, which in our case is a nice tea break. Thank you very much.
Do we have any questions? Yes?
Is it clear, is it obvious you can discard the boundary terms and the integration by parts?
No, not at all. And that's why this Witten wrote a paper of 70 pages to show that indeed, I mean, if you, so what I studied here was because of, this is a very nice, I think, toy, it's not toy model, but it's a limit in which only one dimension survives, only one cross ratio. You can do everything at the level of the two cross ratios, and then this double discontinuity is related to a double commutator of the correlator. And then what happens is that when you are doing these analytic continuations, you are throwing things at infinity, and these things at infinity depend on the Regge behavior of the correlator. So there are assumptions, theorems about the Regge behavior of the correlator, and that is what allows you to say that these boundary terms can be thrown. It also allows you to say that these ambiguities are not too bad. They are ambiguities in spin 0 and 1. And yeah, but indeed, it's a very good question, and that's a problem that has been studied, and that's the final answer, yes.
And those assumption on the behavior at infinity,
Yes.
does it imply something for a bulk theory?
Oh,
Chase away some
yeah, so we will talk about that a lot, actually. Yeah, so I will use this to study holographic conformal field theories in the next lecture. So in the next lecture, we will just study holographic CFT, basically n equals 4, and we will try to guess string amplitudes on a DS5 versus 5. So, you know, that's a problem that you would cry if you have to do it 2 years ago. And now with all these techniques, you can suddenly compute scattering like string amplitudes on curved space-time. So this is the kind of things. And this, I have to say, is a lot of fun. Like you take a paper from the 70s, 80s, you look at the first page, you see what like the spectrum, the symmetries are, you plug these, and in a few hours, you go to the last page of the paper, and you have derived that spectrum. And you know, it's really powerful way of deriving this. No Feynman techniques, you are not using, so this is quite powerful. The hard bit here is to determine the structure of divergences as p goes to 0. And we will talk about this for n equals 4 super n meals, and yeah, but that's the hard bit, yeah.
So I'll cover, I'm glad you did what you did because you saved me a lot of time tomorrow. So now I can finish my lecture. But, so I'll cover a lot of this in 2 dimensions in the context of the disordered
Yes.
field theory. So there you can do a lot of what you've done using the shadow representation for the CFT in 2 dimensions.
Yes.
In which case you would get integral representations for the eigenfunctions of the Casimir.
Right.
And then be able to read off all these properties without writing down a hypergeometric function, for example.
Right.
Can you do the same? Can you extend all that?
Yeah, actually we have done some of these things. Actually, can be done, for instance, in 3 dimensions, and not exactly with the shadow representation, but this you can sometimes do even if you don't know the conformal blocks in a closed form. So you can actually do some progress, but of course at some point it becomes a bit complicated. And for instance, I can tell you with my students, it's something that we are finishing now, but it took us 1 year. We are computing these anomalous dimensions of the critical ON model. And this is in any dimensions between 2 and 4. And if you want to do the diagrammatic computation, it's a 5-loop computation. And you know, here it's not that easy, but it's kind of doable. And that you can do in dimensions between 2 and 4. So you don't need the explicit expression for the conformal blocks. But it's usually, you have to understand how to compute this. And this is sometimes not very easy. Yeah.
Right, If there are no more questions, perhaps we can have a slightly accelerated celebration over tea. And perhaps we should be back at 12:30.
Thank you. Thank you.